this. All right, so hybridization, how does hybridization help us figure out, right, what orbitals we are using, when we're using those orbitals, right? So an example that's different than what we've done in class, we could look at something like acetylene, which I think is one of the exam problems, the practice exam problems. So acetylene is a carbon-carbon triple bond. So the first thing we need to do is figure out, right, what's my hybridization of carbon? Well, I've got two domains on this carbon. So carbon is sp hybridized because we have two domains. This carbon is also sp hybridized because it also has two domains. Hydrogen doesn't need to hybridize. Hydrogen only has an s orbital. It can't hybridize. So we're going to use the s orbital there. We're going to use the s orbital there. So to explain our bonding, right, the hydrogen-carbon sigma bond would be an s orbital from hydrogen overlapping with an sp orbital from carbon. The carbon-hydrogen sigma bond would also be an sp orbital from this carbon to an s orbital from this hydrogen. And I should give myself more space, but the carbon-carbon sigma bond is going to be sp orbital from carbon to an sp orbital to that second carbon, from carbon 1 to carbon 2. And this is important that we're sp hybridized, right? Because if I can draw this out here, right? Here's my carbon, here's my carbon. All right, here's my sp orbital, right? There's my sigma bond right there. I'm going to have hydrogen come in, right? Here's the s orbital of hydrogen. Here's the s orbital of hydrogen. And there's my carbon-hydrogen sigma bond. Okay, so because we're sp hybridized, right? Remember, we have an s and three p orbitals. To become sp hybridized, right, we take one s orbital and one p orbital and blend those together, right? We blended those together. This is important because that tells us we have two p orbitals left over on both carbons, right? Both carbons have an additional p orbital. And that's important because for the pi bond, right, in a triple bond, we have one sigma bond and two pi bonds. So one p orbital, all right, here's one p orbital. It's going to overlap above and below, right, the plane of that sigma bond. So there's one pi bond, p orbital to p orbital. The next one's going to be a little bit harder for me to draw, right, because it should be kind of coming out of the page toward us. So I'll do my best here to draw kind of in three dimensions, not very good. Let's see if I can do this a little bit better. Right, so this is the other p orbital, and now it's going to overlap in front of, right? Basically, imagine it coming out of the screen and then behind the screen. So for my sigma bond, right, sp to sp, and then for my pi bond, right, p orbital to p orbital. For my first pi bond and for my second pi bond, still p orbital to p orbital. So to form our double bonds, in a double bond, we have one sigma. Our sigma bonds can be atomic orbital to atomic orbital to hybrid to hybrid orbital, right? Our pi bonds, we will only see two types of pi bonds. It'll either be p orbital to a p orbital, or like in the case we worked through in class with the sulfate, right? It might be p orbital to a d orbital. Only atomic bonds only atomic orbitals, sorry, can be used for these pi bonds because they're the only orbitals that can overlap in this case, right? They are perpendicular, sorry, they're parallel to each other. They're perpendicular to the sigma bond, right? And so they can allow for this overlap above and below where my sigma bond is, and then out in front, and then behind where my sigma bond is.